Normandy, June 15, 1944. Private First Class Robert Hendricks crouches behind a hedgerow in the French countryside, his hands gripping a weapon that didn't exist 4 years earlier. A weapon so revolutionary that German tank crews who encounter it will describe it as the terror tube in their final radio transmissions. The M1A1 Bazooka rocket launcher weighs just 13 pounds, but the 2.36-inch rocket nestled in its smooth-bore tube carries enough explosive power to punch through 6 inches of hardened steel armor like it was tissue paper. What makes this morning different from countless other engagements is that Hendricks is about to demonstrate why American ingenuity in weapons development has fundamentally altered the mathematics of armored warfare. In his hands lies the culmination of desperate innovation born from America's realization that its pre-war anti-tank weapons were pathetically inadequate against German and Japanese armor. Within minutes, his rocket will transform a 45-ton Panzer IV into a burning funeral pyre, proving that individual infantry soldiers could now destroy the most advanced fighting machines on Earth. The Bazooka's story begins not in the battlefields of Europe or the Pacific, but in the workshops and laboratories of American inventors who understood that conventional warfare was rapidly becoming obsolete. Dr. Robert Hutchings Goddard, the father of American rocketry, had been experimenting with solid-fuel rockets since the 1920s, developing designs that would eventually power everything from anti-tank weapons to spacecraft. His work on rocket-propelled projectiles during World War I laid the theoretical foundation for what would become the most feared infantry weapon of World War II. But it was Captain Edward Uhl, working alongside Colonel Leslie Skinner at Aberdeen Proving Ground in Maryland, who transformed Goddard's theoretical rockets into practical weapons of war. In late 1941, with America's entry into World War II becoming inevitable, Uhl recognized that existing anti-tank weapons, the 37mm anti-tank gun and various anti-tank rifles, were already obsolete against German armor improvements. German engineers had steadily increased tank armor thickness throughout the 1930s, and by 1941, even the Wehrmacht's medium tanks carried frontal armor that could deflect most American anti-tank rounds. The breakthrough came when Uhl examined captured German Panzerfaust designs and realized that shape-charge warheads could achieve penetration that kinetic energy weapons could not. The physics of shape charges, discovered by American scientist Charles Edward Munro in the 1880s, involved focusing explosive energy into a narrow jet of superheated metal that could burn through armor regardless of the weapon's size or the projectile's velocity. A properly designed shape charge could penetrate armor thickness many times greater than the charge's own diameter, meaning that a relatively small rocket could destroy tanks that weighed dozens of tons. Working with urgency born from reports of German tank superiority in North Africa, Uhl's team developed the M1 rocket launcher in just 6 weeks during the spring of 1942. The weapon consisted of a simple steel tube 54 inches long, weighing 18 pounds when loaded, with a basic electrical firing system that used flashlight batteries to ignite the rocket motor. The rocket itself, designated M6A1, contained 8 ounces of Composition B explosive in a shape-charge warhead that could penetrate 4.7 inches of homogeneous armor plate at optimal range. The simplicity of the Bazooka's design masked sophisticated engineering solutions to complex ballistic problems. The rocket's stabilization system used 4 spring-loaded fins that deployed after leaving the launcher, providing gyroscopic stability that kept the projectile on target at ranges up to 400 yards. The shape-charge warhead featured a copper cone liner that, when detonated by the base-mounted fuse, formed a coherent jet of molten metal traveling at speeds exceeding 25,000 feet per second, fast enough to penetrate the hardest tank armor by literally melting through it. American manufacturers scaled up production with characteristic industrial efficiency, with General Electric producing the launchers and Bendix Corporation manufacturing the rockets. By late 1942, production lines were delivering thousands of bazookas monthly, but the weapon's true effectiveness would only be proven in combat, where theoretical penetration values would meet the reality of battlefield conditions and enemy countermeasures. The bazooka's combat debut came in November 1942 during Operation Torch, the Allied invasion of North Africa, where American forces encountered German armor for the first time in significant numbers. Lieutenant Colonel William Darby's Rangers carried the new weapons ashore at Arzou, Algeria, where they would face their first test against Vichy French tanks defending the coastal fortifications. The initial engagements revealed both the weapon's devastating potential and the need for improved training in its employment. Sergeant James Mitchell of the 1st Ranger Battalion recorded the first confirmed bazooka kill during the assault on Arzeau's harbor defenses, when his rocket struck a French Renault Arz-35 light tank at 150 yards, penetrating the turret and detonating the ammunition storage. The explosion lifted the 10-ton tank's turret completely off its hull, demonstrating the weapon's ability to achieve catastrophic kills against armored vehicles. Mitchell's after-action report described the psychological effect on both sides. The French tank crew had no idea what hit them. One second they were firing at us, the next second their tank just exploded. Our own guys were amazed. None of us really believed this thing would work that well. But the weapon's early employment revealed significant tactical challenges that would require months of combat experience to solve. The bazooka's backblast created a signature that revealed the operator's position to enemy forces, making immediate relocation essential for survival. The weapon's minimum arming distance of 30 yards meant it was useless in close quarters combat, and its relatively slow rocket velocity, 284 feet per second, required operators to lead moving targets significantly. Most critically, the shaped charge warhead was sensitive to impact angle, losing effectiveness dramatically when striking armor at oblique angles. These lessons became crucial when American forces moved into Tunisia and began facing German Afrika Korps units equipped with Panzer III and Panzer IV tanks. German tank commanders initially dismissed reports of American rocket weapons, assuming they were dealing with conventional recoilless rifles similar to their own Panzerschreck. This misconception proved fatal during the Battle of Sidi Bouzid in February 1943, when Staff Sergeant Anthony Ritchie's bazooka team destroyed 3 Panzer IVs in rapid succession, each rocket striking the tank's side armor at optimal angles and achieving complete penetration. The German response was swift and systematic. Tank crews began employing more dispersed formations to prevent multiple vehicles from being engaged by single bazooka teams, while infantry support was increased around armored units to suppress American rocket teams before they could fire. German engineers also began developing countermeasures, including standoff armor and track guards designed to detonate shaped charge warheads at suboptimal distances from main armor belts. Major General Lloyd Fredendall, commanding the Artillery Corps, recognized that the bazooka's effectiveness depended heavily on proper tactical employment and intensive training. He established specialized anti-tank training centers in Algeria, where infantry squads learned to coordinate bazooka attacks with rifle fire, smoke screens, and artillery support. The training emphasized patience and target selection, teaching operators to wait for optimal shots at close range rather than engaging targets beyond the weapon's effective envelope. By the time American forces participated in the final push against Axis forces in Tunisia, bazooka teams had developed sophisticated tactics that maximized the weapon's lethality while minimizing exposure to enemy fire. Teams operated in pairs, with one soldier carrying the launcher and rockets, while his partner provided security and target designation. Advanced teams learned to coordinate multiple simultaneous attacks against single targets, ensuring kills even if individual rockets missed or failed to penetrate effectively. The North African campaign validated the bazooka concept while revealing areas for improvement that would influence subsequent development. Combat reports emphasized the need for improved training, better rockets with enhanced penetration, and modified launchers that could be operated more effectively in various terrain conditions. These lessons would prove crucial as American forces prepared for operations against Japanese positions in the Pacific, where the weapon would face entirely different tactical challenges. The Pacific theater presented unique challenges that would push bazooka development in unexpected directions. Unlike the open tank country of North Africa and Europe, Pacific islands featured dense jungle, steep terrain, and extensive fortifications that required different tactical approaches. Japanese defenders had learned from German experiences with American rocket weapons, developing countermeasures and tactical responses that would test the bazooka's versatility beyond its original anti-tank role. Tarawa Atoll, November 20, 1943. Marine Corps Staff Sergeant Daniel Yamamoto, leads his fire team across the blood-soaked coral of Red Beach 2, carrying an M1A1 bazooka that weighs more than his rifle, but represents the only effective weapon against the Japanese concrete bunkers that have turned the beach into a killing field. The Japanese have constructed their positions using reinforced concrete up to 8 feet thick, far beyond the penetration capability of standard rifle grenades or demolition charges that individual Marines can carry and employ under fire. What Yamamoto understands, and what Japanese defenders could not have anticipated, is that the bazooka's shaped charge warhead is equally effective against concrete fortifications as against tank armor. The physics of shaped charge penetration work just as well on reinforced concrete as on hardened steel, creating precisely the kind of breaching capability that amphibious assault forces desperately need against heavily fortified positions. The Japanese defense of Tarawa had been designed around the assumption that American forces would rely on naval bombardment and conventional explosives to reduce fortified positions, allowing defenders to shelter in deep bunkers during the preliminary bombardment and emerge to man their weapons when the assault began. Japanese engineers had constructed interlocking fields of fire, using concrete bunkers positioned to provide mutual support, with each position designed to withstand direct hits from 16-inch naval guns through depth and deflection, rather than just thickness. But the Marines' employment of bazookas at close range against embrasures and wall junctions created vulnerabilities that Japanese engineers had not anticipated. Sergeant Yamamoto's first rocket, fired at just 50 yards against the main gun port of a Japanese bunker, penetrated the concrete completely and detonated inside the position, killing the entire crew and destroying their 75mm gun. The psychological effect on surrounding Japanese positions was immediate and devastating, as defenders realized that their concrete protection could be breached by individual Marines carrying portable weapons. Marine Corps combat engineers quickly recognized the bazooka's potential for bunker-busting operations and began developing specialized tactics for Pacific operations. Teams learned to approach fortified positions using available cover, engage embrasures and vision ports at close range, and coordinate rocket attacks with flamethrower assaults to clear positions completely. The weapon's ability to create precise breaching holes in concrete made it invaluable for clearing cave systems and underground positions that dominated Japanese defensive strategies. The success at Tarawa led to expanded bazooka employment throughout Pacific operations, but also revealed the need for improved ammunition designed specifically for fortification reduction. The standard M6A1 anti-tank rocket, while effective against concrete, lacked the explosive effect needed to ensure complete destruction of bunker complexes. American ordnance specialists responded by developing the M6A3 rocket, which featured an increased explosive charge and modified fusing, designed to maximize blast effect inside confined spaces. Japanese forces responded to American rocket weapon employment by modifying their defensive tactics and fortification designs. Bunkers began incorporating angled approach barriers designed to force bazooka teams into exposed positions, while defensive positions were equipped with additional automatic weapons, specifically tasked with suppressing American rocket teams. Japanese engineers also began designing bunkers with multiple compartments and blast doors, limiting the damage that single rocket hits could achieve. The Battle of Saipan in June 1944 demonstrated how both sides had adapted to rocket warfare in the Pacific. Japanese defenders employed more sophisticated camouflage and decoy positions to make target identification difficult, while American forces used concentrated rocket attacks supported by armor and artillery to systematically reduce fortified positions. Marine bazooka teams developed techniques for attacking bunkers from multiple angles simultaneously, ensuring that at least one rocket would achieve effective penetration, even against improved Japanese defensive positions. By late 1944, the bazooka had become as important for Pacific operations as it was for European theater anti-tank warfare. Marine and Army units carried the weapon specifically for bunker reduction, and specialized training centers in Hawaii and Australia taught infantry units the tactics needed to employ rockets effectively against fortified positions. The weapon's versatility had proven that shaped charge technology could revolutionize infantry capabilities far beyond its original anti-tank mission. When the M6A3 rocket's 8.5 ounces of composition bay explosive detonated, the blast wave traveled through the warhead at approximately 26,000 feet per second, striking the copper liner and collapsing it inward at precisely calculated angles. The collapsing copper formed two distinct components: a high-velocity jet traveling at speeds up to 30,000 feet per second, and a slower-moving slug that followed behind at roughly 2,000 feet per second. The jet, containing about 20% of the original liner mass, provided the penetrating capability, while the slug delivered additional kinetic energy inside the target. The physics of jet formation required extraordinary precision in manufacturing and quality control. Variations in explosive density, liner thickness, or standoff distance could reduce penetration dramatically or cause complete warhead failure. American manufacturers developed sophisticated testing procedures to ensure consistent performance, including X-ray inspection of explosive charges and precision measurement of copper liner dimensions. Quality control became so stringent that rejection rates for completed rockets sometimes exceeded 15%, with defective rounds returned for complete remanufacturing. The jet's interaction with armor involved temperatures exceeding 1,000 degrees Celsius and pressures approaching 5 million pounds per square inch, conditions that caused steel armor to behave more like liquid than solid material. The jet didn't actually melt through armor in the conventional sense, but created a localized zone of extreme pressure and temperature that allowed the metal to flow around the penetrator like thick fluid. This explained why shaped charges could defeat armor far thicker than the jet's length, and why penetration was relatively independent of armor hardness. German metallurgists, studying captured Bazooka rockets, initially dismissed American shaped charge technology as inferior to their own Panzerfaust designs. This misconception proved costly, as German engineers underestimated the precision and consistency of American manufacturing. While German shaped charges often achieved higher theoretical penetration values, they suffered from greater variability and lower reliability than American rockets. The difference lay not in understanding the physics, but in the industrial capability to produce consistent high-quality warheads in massive quantities. The standoff distance between warhead and target proved critical to achieving optimal penetration. Bazooka rockets were designed to function at standoff distances between 6 and 12 inches, allowing the shaped charge jet to form completely before striking armor. Contact detonation or excessive standoff reduced penetration significantly, forcing American engineers to develop sophisticated fusing systems that ensured optimal detonation timing regardless of impact conditions. Advanced shaped charge designs introduced during 1944 incorporated multiple innovations that increased penetration while reducing manufacturing complexity. The M9A1 rocket featured an improved copper liner with variable wall thickness that optimized jet formation, while the explosive charge was reformulated to achieve more consistent detonation velocity. These improvements increased penetration from 7.5 inches to 11 inches, while actually reducing the explosive charge weight through more efficient energy utilization. The temperature and pressure conditions inside the shaped charge jet also explained why Bazooka rockets were equally effective against concrete fortifications and steel armor. Reinforced concrete, with compressive strength around 4,000 pounds per square inch, simply could not resist the extreme conditions created by jet formation. The jet burned through concrete and steel reinforcement with equal ease, making the Bazooka as effective for bunker busting as for tank destruction. Japanese and German attempts to develop countermeasures against shaped charges focused on disrupting jet formation through standoff armor, cage armor, and spaced plate systems. These measures achieved limited success against early American rockets, but the introduction of improved warheads with enhanced standoff tolerance and multiple stage designs overcame most passive countermeasures. The fundamental physics of shaped charges made them nearly impossible to defeat without extremely complex and heavy armor systems that compromised vehicle mobility and production efficiency. The transformation of the Bazooka from experimental weapon to standard infantry equipment required an unprecedented industrial mobilization that demonstrated American manufacturing capability at its peak. Within 18 months of the weapon's approval for production, American factories were delivering bazookas and ammunition at rates that supplied not only US forces worldwide, but also Allied armies from Britain to the Soviet Union. This logistical achievement represented one of the war's most successful technology transfer programs, putting advanced anti-tank capabilities into the hands of infantry forces that had previously been helpless against armored attacks. General Electric's Schenectady plant became the primary bazooka launcher manufacturer, converting production lines previously used for electrical equipment to weapons manufacture with remarkable efficiency. The company's engineers redesigned the launcher for mass production, simplifying the electrical firing system and developing manufacturing techniques that could produce finished weapons from raw materials in just 4.2 hours per unit. By peak production in mid-1944, General Electric was delivering 8,000 launchers monthly, while maintaining quality standards that kept weapon failure rates below 2%. The rocket manufacturing program proved even more complex, requiring coordination between multiple suppliers and sophisticated quality control systems. Bendix Corporation produced the rocket bodies and fin assemblies, while explosive charges came from DuPont facilities in Delaware and Tennessee. The critical copper liner cones were manufactured by American Brass Company, using precision techniques developed specifically for shape charge applications. Final assembly occurred at facilities in Ohio and Michigan, where completed rockets underwent testing that included live fire-proof rounds to ensure batch consistency. Quality control standards for bazooka ammunition exceeded those of most artillery shells, reflecting the weapon's reliance on precise shape charge physics for effectiveness. Every batch of completed rockets underwent ballistic testing, with random samples fired against standardized armor plates to verify penetration performance. Manufacturing tolerances for copper liners were measured in thousandths of an inch, requiring precision machining techniques that pushed American industrial capability to its limits. The explosive charges received particular attention, with X-ray inspection used to detect air bubbles or density variations that could cause warhead failure. Distribution of bazooka weapons required coordination between multiple military services and allied nations, each with different training requirements and tactical doctrines. The U.S. Army established standardized training programs at infantry schools, while the Marine Corps developed specialized courses for Pacific operations. British forces received both weapons and training materials through Lend-Lease, adapting American tactics to Commonwealth military doctrine. Even the Soviet Union received limited quantities of bazookas, though Soviet engineers quickly developed their own improved versions based on captured German Panzerschreck designs.